Welcome to the complete guide on limits for Calculus 1. This video is a compilation of my past limit lessons. If you'd like to go to any of them individually, you can check out this timestamps in this video, or you can check out the Calculus 1 playlist, which is linked here. Enjoy the video. Welcome to Limits Introduction and welcome to Calculus. This is the first thing you learn in calculus, so I'm going to write it down up here just so you remember what you're learning. We are learning the very basics of limits today. Limits are the fundamental building block of all of calculus. And even after this lesson, that may sound a little bit weird, but as you get further in calculus, this will make more and more sense. Let's start with an example problem. A train is leaving Gotham City because, let's be honest here, who would want to live in Gotham City, right? At 54 miles per hour. And we want to figure out how far will that train go in 3.2 hours? Now you may be looking at this question and thinking, yeah, that's really easy. And you'd be right, it is a really easy question. All we have to do is multiply 54 times 3.2. 54 miles times 3.2 hours. When we multiply 54 times 3.2, our answer comes out to be 172.8 miles in the allotted 3.2 hours. So why do I bring up this example? This is clearly not a calculus problem. Well, I want to bring up the idea of the limit. This is the farthest the train can go, going 54 miles an hour in 3.2 hours. This is not how far it will go. It's not a guarantee. Like, what happens if our train here, he's going along the track and boom, he gets blown up by I don't know, some bandits or something. That could be a problem, right? What if the train gets off to a really slow start? It doesn't start on time. Maybe somebody's late, maybe the conductor fell asleep at the wheel. I don't know. Regardless, we're not guaranteed to go the full 172.8 miles. And that's where the idea of the limit comes in. Let me explain. Let's use a function we all know. We're going to use the function y equals x squared. We all know what that looks like, right? We have our graph here, and let me take this green pen. It looks something like this, that, and that. It's an even curve on both sides. So here's the question. What is the limit as x approaches 2 of x squared? Now, since you're new to calculus and watching this video, you may not know what that answer is. And trust me, I didn't know what it was either. This stuff was very confusing when I first learned it, and I want to make it simple. Well, it turns out this answer is actually pretty easy to get to. All we have to do is figure out what our function equals at x equals 2. So this is x equals 2 along the x-axis. What does our y value equal? If x equals 2, what does our y value equal? We can find that simply by plugging in 2 into our function. So y is equal to 2 squared, which is equal to 4. So the limit as x approaches 2 of x squared is just equal to 4. Pretty easy, right? This is the basic idea of limits. Essentially, we want to figure out what happens when we get really close to a certain point on our function. As our function gets closer and closer to equaling x equals 2, our function gets closer and closer to equaling y equals 4. That is the basic idea of limits and what we will be basing the rest of calculus on. It may sound crazy that such a simple concept is what calculus is based on, but trust me, it makes more sense as we get further along. For today, we're just going to work with simple limit problems like this one. Let's try something a little bit more difficult. Here we have the function f of x, remember that's basically the same thing as y, is equal to sine of x divided by x. And we want to find the limit as x approaches, that's what this arrow means, approaches 0. So we could try what we did before. We could plug in 0 to our function, and we get sine of 0 divided by, ooh, that could be a problem. We can't divide by 0. That's not allowed. Imagine trying to show off a collection to 0 people. How do you even divvy that up? You can't. There's nobody to show it to. We cannot divide by 0. So how do we solve this problem? Good question. Well, what we can do is draw the graph of this problem. The graph looks like this. So our sine function, it goes whoop and hits this spot here and goes back down and repeats like that forever. You may notice here at x equals 0, we have a hole in our function. This hole means that we don't actually have something that exists at x equals 0. But you may remember a key word in something I said earlier. We don't care what happens when we actually reach x equals 0. We just care what happens as we approach x equals 0. So as our line gets closer and closer to equaling x equals 0, what does our y value equal? Well, we can figure this out by plugging in numbers that are very close to 0 to our function. So let's try something such as sine of 0.001 divided by 0.001. Now, as you can see, we're not dividing by 0 anymore, which means this function is valid. We can figure out what that equals. And this is extremely close to equaling 1. So the limit as x approaches 0 of our function sine of x divided by x is equal to 1. See, not too bad, and it's even easy to see visually. Before we go too much further, I do want to talk about limit notation, because there's a certain way you're supposed to write down these problems, and I haven't been doing that so far. So here's limit notation. We write LIM, that stands for limit, and then right underneath that we write x, or whatever variable we're using. It could be z, it could be y, it could be, I don't know, a Greek letter like alpha or something, I don't know. It could be anything. Write an arrow, that stands for approaches. The limit as x approaches, and then our c, which is just some constant number, such as 0.5, 2, 69, 387.2, whatever you want. And then here we'll write our function. Remember, f of x is just a function. So this is read as the limit as x approaches c of our function, and that all equals big C, which is just whatever our limit is. Using the example we just did, the limit as x approaches 0 of sine of x divided by x is equal to 1. Let me read that again for you. The limit as x approaches 0 of sine of x divided by x is equal to 1. Let's do another limit problem, but this time the graph is going to be very hard to visualize. Here's the limit we want to find. We want to find the limit as x approaches -2 of x squared plus x minus 2 divided by x plus 2. What is the limit? So the first thing you may notice is if we were to just plug in x for all these numbers, we get -2 plus 2, which is 0. Once again, still can't divide by 0. That hasn't changed in the last 3 minutes. And also, this graph is not easy to visualize. I don't know what this looks like. I know you don't know what this looks like. So what we're going to do is we're going to implement the strategy we used earlier. We're going to plug in a lot of numbers that are very close to -2 and see what happens. Over here, I'm going to draw a little chart of what numbers we used and what limit we got. So we're going to write our x, whatever we plugged in, and our f of x, whatever the output is. First, we're going to try -2.3. We're going to try that first. So if we plug in x is equal to -2.3, all we have to do is replace every x in here with -2.3. So this will equal -2.3 squared plus a -2.3 minus 2 divided by -2.3 plus 2. I'm not going to do all the simplification here, but what this ends up equaling is -3.3. So let's write that down over here, -3.3. Next, let's try something even closer to -2, such as x equals -2.1. Let's do the same process. -2.1 squared plus a -2.1 minus 2 is equal to -2.1 plus 2. Once again, I'm not going to show the simplification, but this is equal to -3.1. You may notice that we're approaching a number, but we're going to check a couple more things first. So I'm going to write it down in our little graph here, -2.1, -3.1. Okay, let's plug in something extremely close to -2, such as -2.001. That's pretty close to being -2, but it's not, so we won't end up dividing by 0. Plugging in x equals -2.001, we get -2.001 squared plus a -2.001 minus 2, all divided by -2.001 plus 2. And you may be noticing a pattern here. This is going to equal a -3.001. Let's write it down over here. -3.001. You might have an idea of what our limit is, but we're going to try one more number, and we're going to try something slightly bigger than -2. We're going to try -1.997. That's slightly above -2, but once again, we will not divide by 0. So let's try that. X equals -1.997. Plugging this in, we get -1.997 squared plus a -1.997 minus 2 divided by -1.997 plus 2. Once again, not going to do the simplification for this fraction, but this ends up equaling -2.997. -2.997. I think you guys may have noticed a pattern. We're getting closer and closer to -3 every time we get closer and closer to -2. So because we're getting closer and closer to -3, the limit as x approaches -2 of x squared plus x minus 2 divided by x plus 2 is equal to negative 3. Boom. Easy. That's not hard at all. Before we end this video, I want to show you one more thing with limits. What we're going to do is we're going to look at a limit, and we're not even going to have a function. We're not going to have an f of x equals x squared or anything like that. We're only going to have a graph, and we're going to solve that limit. So this graph is a piecewise function. Remember, a piecewise function is two functions kind of smushed together. So in this example, we have this, and we have this. And there's 2 points of interest for us. We have the point down here, 0, negative 2, and the point up here, 0, 2. Both of these functions are extending to negative infinity and infinity respectively. What is the limit as x approaches 0 of our piecewise function here? What we're going to learn about here is the left and right side limits rule. The left and right side limit rule. What this says is that we need to find two different limits. In order for a limit to exist in the first place, the limit coming from the left side and the limit coming from the right side have to be the same. So what we're going to do here is actually find two limits. So we're going to denote this as limit as x approaches 0 from the positive side, in other words coming from there to there, and limit as x approaches 0 from the negative side, in other words here to there. And since we have a graph, it actually is pretty easy to find both of these limits. Let's start with coming from the positive side. We start at infinity and approach 0. So here's x equals 0 along this line. And as we approach from negative infinity all the way to 0, as x gets closer and closer to equaling 0, our y gets closer and closer to equaling 2. This is a constant function. Now let's do it from the negative side. Starting at negative infinity, coming closer and closer to x equals 0. As we get closer and closer, our y gets closer and closer to equaling negative 2. Now remember what I said earlier. The left and right side limits have to be the same in order for the limit to exist. So, does 2 equal negative 2? No, of course not. They're not the same number at all. So, the answer to this question is not an answer at all. The answer is that the limit as x approaches 0 of this function we wrote up here does not exist, or DNE for short. And I use this example to show that limits just don't always exist. There doesn't always have to be a limit. There's plenty of functions that just straight up don't have limits, such as this one. And in future limit videos, we'll talk about continuity and some other things that will show if our function has a limit or not in the first place. Today we're going to be talking about properties of limits. In other words, what can we do, or what do we know about limits that can help us make these problems a little bit easier to solve? Properties of limits, that's what we're going to be talking about today. And there's 7 properties that we're going to go over in this video. Let's get started with rule number 1. Rule number 1 is the law of constants. Law of constants. The law of constants states that if your limit, let's just say, as x approaches some constant of a constant, in this case k, so something like 7, 3.5, 69, 1 billion, whatever that constant is, if your function is also a constant, the limit, no matter what, is just the constant. This is a little bit easier to see visually. Let me pull out my red pen. If we have a graph such as this, a constant function looks like this. Let's just say this is y equals 3. The constant function y equals 3 from negative infinity to infinity. It looks like that. So no matter where you approach along this line, you're just going to get 3. So let's say we had the limit as x approaches 1. No matter where you're approaching along this line, you're just going to approach y equals 3 because, well, it's the same. It's a constant. Nothing changes. If I say we approach, x equals negative 2. Let's say that's x equals negative 2. Turns out that this line is still y equals 3. So even though we're approaching a completely different number in a completely different spot in the graph, our limit is the exact same because, well, the function is constant. This is a pretty easy one to understand visually. I'm going to do a written example just to make the point even more clear. Let's say we had the limit as x approaches 7 of 10. What is that limit equal to? Well, we know based on our rule that the limit of x approaching anything of k, and k being our constant, is just equal to the constant. So this limit is just 10. Our second property of limits, law number 2, is the law of the x function. This law states that the limit as x approaches some constant c of the function x, this will always equal whatever x is approaching. This is another law that's easy to understand visually. Using the graph of the xy plane, we know that our function x is the same thing as just y equals x. That's what this means. Y and x are just the same, which means our graph looks like this. Just from negative infinity to infinity going along this diagonal line where y is equal to x. If x is approaching some value, I don't know, let's just say this is 2. Well, since we know that y and x are equal to each other, y will equal 2 and our limit will equal 2. That's what this law states. Let's do one mathematical example. If we have the limit as x approaches, I don't know, 7 of x, what does this limit equal? Well, by our law, we know that whatever x is approaching is the limit of the x function. So this limit is just equal to 7. Those first two are fairly easy to understand. The next few will be a bit more complicated, but trust me, they're not too bad either. Our third law is the law of scalars. And this law states that the limit as x approaches c of k, which is some constant, times f of x, which is our function, is equal to the limit as x approaches c of f of x, all multiplied by k. In other words, we can pull a constant or a scalar out of the function and bring it to the front. What this allows us to do is find out what the limit is first, and then simply multiply it by whatever we pulled out to the front. Let's use an example. Let's say we have the problem, the limit as x approaches 2 of 3x. What is this limit equal to? Let's use our law of scalars. As you can see, this is being multiplied by our entire function, which is just x, which means we can pull it to the front as such. So this turns into 3 times the limit as x approaches 2 of x. Remember, our second limit law states that if our function is just x, whatever x is approaching is just the limit. So this limit is just equal to whatever x is approaching, which is 2. Which means that this is just equal to 3 times 2, which is equal to 6. Let's do one more example, just to really hammer the point home. Let's do the limit as x approaches 7 to x squared. Let's try something a little different. What is the limit of this problem? Well, once again, you may notice that we have a number that's being multiplied by the entire function, which means, once again, we can pull it out of the limit, or to the front of the limit, whichever terminology you would like to use. So then this turns into 2 times the limit as x approaches 7 of x squared. Now, what is the limit as x approaches 7 of x squared? That's a good question. For this problem, what we can do is plug in 7 for x. That's how we can solve most limit problems. So what we're going to do is multiply 2 by 7 squared. 7 squared is 7 times 7, which is equal to 49. So this is equal to 2 times 49, and 2 times 49 is simply equal to 98. So that is the limit as x approaches 7 of 2x squared. This is another concept that's pretty simple, and trust me, will save you a lot of time and a lot of headaches with bigger numbers. Now we're going to move on to laws that are almost the exact same with one minor difference. So limit law number 4 is the law of addition. Law of addition. And limit law number 5 is the law of subtraction. Now the law of addition states that the limit as x approaches some constant c of f of x plus g of x is the same thing as the limit as x approaches c of f of x plus the limit as x approaches c of g of x. And similarly, the law of subtraction is the same thing but with subtraction. So the limit as x approaches c of f of x minus g of x is the same thing as the limit as x approaches c of f of x minus the limit as x approaches c of g of x. Of g of x. In other words, this is stating that we can split limit problems by addition and subtraction, and sometimes this makes it a little bit easier to solve. Let's do one simple example for both of these. And you know what? Let's spice it up. Instead of using the black pen, we'll use the green one for a little bit. For the law of addition, we have the limit as x approaches 3 of 3x plus x squared. What is the limit of this function? Well, as we just discussed, we can split this up by addition, and we have an addition sign right there. So let's split it up. The limit as x approaches 3 of 3x plus the limit as x approaches 3 of x squared. These are equivalent. So now, like I mentioned earlier, we can just plug in whatever x is approaching to whatever x is within our limit. Let's do that here. We can plug in 3 times 3x, so this will be 3 times 3. Wow, that's really thick. And then we can add 3 squared, so 3 squared. 3 times 3 is equal to 9, and 3 squared is the same thing as 3 times 3, and so that's also equal to 9. So 9 plus 9 is equal to 18. And that is the limit of our function. Let's do a slightly different example for subtraction, and I'll even use the red pen for funsies. Let's find the limit as x approaches 1 of x squared minus 7. What is the limit of this function? Well, based on our law of subtraction, we can split this up by subtraction. And as you can see, we have a minus symbol right there. So let's split it up at that point. So the limit as x approaches 1 of x squared minus the limit as x approaches 1 of 7. This is equivalent to that based on our law of subtraction. Let's find both these limits. Here we can just plug in 1 to x squared because x is approaching 1. So let's plug it in there. And remember, we just learned about the law of constants. No matter what x is approaching, if our function is a constant, the limit of that function is the constant. So here we have 1 squared, and the limit as x approaches 1 of a constant is just the constant, and our constant here is 7. So 1 squared minus 7. 1 squared is the same thing as 1 times 1, which is just 1, and 7 is just 7, so 1 minus 7 equals negative 6. And that is the limit of the function. Like I said, these are extremely similar, but the upside to that is that they're very easy to remember. Our sixth law, law number 6, is the law of multiplication. And this is a long word, so give me a second. Multiplication. Law number 6, law of multiplication. You may be able to guess what this law looks like. If we have the limit as x approaches c of f of x, which is function number 1, times g of x, function number 2, we can split it up by multiplication just like we did for addition and subtraction. So this is the same as the limit as x approaches c of f of x times the limit as x approaches c of g of x. Like I said, very easy to remember since it's the same as addition and subtraction. Let's do an example of this, and to spice it up even more, we're going to use the blue pen. That's new. Blue pen, blue pen, blue pen. Let's write our example. Let's find the limit as x approaches 2 of 3x times x plus 7. So let's split these two up by multiplication, since, well, we can. Let's find the limit as x approaches 2 of 3x, and then multiply that by the limit as x approaches 2 of x plus 7. Once again, we can just plug in whatever x is approaching to our limit function, and that will give us the limit of that function. So let's do that for both of these. The limit as x approaches 2 of 3x is equal to 3 times 2 when we plug in 2 for x, and the limit as x approaches 2 of x plus 7 is just, well, 2 plus 7. Let's simplify these down a little bit. 3 times 2 is equal to 6. 2 plus 7 is equal to 9. Now that we simplified it down, 6 times 9 is just equal to 54. 54. And that is the limit of this problem. Not so bad, right? Now at this point in the video, it may seem a little bit like these properties are just kind of useless knowledge that you need to know. Now, I counter that by saying that knowing these properties of limits will let you know what you can do to make a limit problem easier. And that's where I find the most use out of these. Knowing what we can actually do with a limit gives us new strategies to solve limits more easily, even if they're very complex. And I'll go over that in the next limit lesson, but let's finish this one first. I'll link it in the top right corner in case you want to skip ahead to that lesson, but you should stick around. There's just a little bit more to learn. You're almost done. Property number 7 is the law of division. And shocker, it's very similar to the other 3 we just did. The law of division states that the limit as x approaches some constant of f of x, function number 1, divided by g of x, function number 2, can be split up and is equal to the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. But there is one more rule tacked onto this. In math, we can't divide by 0. It just doesn't make sense. It doesn't work. So your limit as x approaches c of g of x cannot equal 0. So I just want to make a note here that the limit as x approaches c of g of x cannot equal 0, or else this will not work. Let's do an example. May as well use the blue pen again. It worked so well last time. Let's find the limit as x approaches 1 of 4x divided by 7x squared. At first glance, this may look a little intimidating, but because of our rule, we can make it a lot less intimidating and just a little easier to solve. So let's do that. Let's split up our two functions by their limits. So this is the same thing as the limit as x approaches 1 of 4x divided by the limit as x approaches 1 of 7x squared. And just like we've done in our past examples, in order to fully solve these limit problems, we can just plug in whatever x is approaching for x to get our limit. So this is equal to 4 times 1 divided by 7 times 1 squared. Now this is much easier to solve and just looks a little nicer. So now all we have to do is simplify our question down. 4 times 1 is just equal to 4. 1 squared is just equal to 1, and 1 times 7 is just 7. So the limit of this problem is 4 7s. All right, you stuck around this far. We only got one more limit law to go. May as well get it out of the way. Our last limit law number 8. I think I said 7 in the beginning. I was kidding. In my notes, I combined addition and subtraction, but I made them separate here. Limit law number 8 is the law of exponents. The law of exponents. What does the law of exponents state? That's a great question. Let's write it down here. The limit as x approaches c of f of x squared, whatever our function is squared, can be changed into the limit as x approaches c of f of x squared. But you may notice one crucial difference. If our exponent is applied to the entire f of x function, we can apply it to just the limit as a whole. In other words, we can pull it out of the limit just like we did with constants earlier. And I want to make that very apparent. Your exponent has to apply to your entire function within the limit and not just part of it. So as a little example to get my point across, the limit as x approaches 1 of x squared plus 3x cubed, we would not be able to apply the law of exponents in this form because we have two exponents that are both not being applied to the whole function. We could solve this using the law of addition and then using the law of exponents, but we're not going to do that right now. We're going to do a different example that I think will help you out more in the rest of calculus. So I'm going to erase this here to give myself a little extra room. Let's solve the limit as x approaches 1 of the square root of x plus 3. Now why did I choose a square root? Well, if you don't know, a square root can be rewritten. So let's say we have the square root of x. This can be rewritten as x to the 1/2 power. This is a trick that will come in handy many times in calculus, so be sure to remember it, because I will probably also use it in further examples in this video series. But for now, let's solve this problem. Since we just learned about this law, let's convert this square root into the 1/2 power. So this is the same thing as the limit as x approaches 1 of x plus 3 to the 1/2 power. Now that we have an exponent that applies to our entire function, we can pull it out of the limit. So this is now equal to the limit as x approaches 1 of x plus 3 all to the 1/2 power. Now we can more easily visualize this limit problem. Once again, like we've been doing throughout the rest of this video, we can plug in whatever x is approaching to x to solve for our limit. This is equal to 1 plus 3 to the 1/2 power. 1 plus 3 is just equal to 4 to the 1/2 power, which, remember, the 1/2 power is the same as the square root. So we get the square root of 4, which is just equal to 2. And that is the limit of our problem. In today's limit lesson, we're going to learn about factoring limits. Now, what do I mean by this? Well, limit problems are not terribly hard to solve, if you ask me. But we can always make them simpler, and that's always a good thing to be able to do. You probably learned what factoring was in Algebra 1, maybe Algebra 2. So, say we have a problem like x squared plus 6x plus 9 is equal to 0. We can simplify this problem and make it much easier to solve by factoring it. In this case, our factors are x plus 3 and x plus 3 are equal to 0. Now that we have our factors, we can set each individual factor to 0. So x plus 3 is equal to 0 and x plus 3 is equal to 0. And of course, to solve this problem, we would just subtract 3 from this side, so then x is equal to -3. We can use the fact that we can split this up and factor it in order to make solving some limit problems a little bit easier. Let's do a couple examples to show you what I mean. Our first example will be x squared minus x minus 6 divided by x minus 3. What is the limit of this problem as x approaches 2? What is that equal to? Now, at first glance, this is a lot of math that we just don't really want to do. But we can make this a lot simpler really quickly. You may notice that in the numerator of this function, we have a function that looks a lot like the form ax squared plus bx plus c. And if we have a function in this form, in other words, we have a squared factor, just the variable, and then a constant, we can factor it. So let's do the factorization of this problem. X squared minus x minus 6 equals 0. So my question to you, what are two numbers that add together to equal -1 and multiply to equal -6? That will give us our factors and make this problem much simpler. I'll give you a hint, you already know one of the factors because of how this problem is set up. Think you've thought of that factor? Well, one of our factors is just going to be this bottom function. The idea with factoring for limits is that we can cancel something out, and in this case with division, we're probably going to want to cancel out whatever is on bottom. So we know that one of our factors is x minus 3. So what would our other factor be? What other number, along with -3, could be used to add up to equal -1 and multiply to be -6? If you said positive 2, you are correct. Just to double check this, x times x is x squared. You say x times x is x squared. X times 2 is 2x. -3 times x is minus 3x. And -3 times 2 is -6. Add these two together, we get x squared minus x minus 6, which is the same as we started with. So we can replace our numerator, which was this x squared minus x minus 6, with our new factored function. This will turn into the limit as x approaches 2 of x minus 3 times x plus 2 divided by x minus 3. Now here's the cool part. You may notice that we have an x minus 3 and an x minus 3, one on top and one on bottom, which means we can cancel that out. And this makes our problem so much easier. This turns our problem into the limit as x approaches 2 of x plus 2. And this is much simpler to solve. All we have to do is plug in 2 as x is approaching 2. We just have to plug in whatever x is approaching to our limit function to solve for our limit, which is equal to 2 plus 2, which of course is equal to 4. So the limit as x approaches 2 of x squared minus x minus 6 divided by x minus 3 is equal to 4. Let's do two more examples just to get the idea down. Let's do the example of, our next example will be the limit as x approaches 1 of x squared minus 2x minus 15 divided by x minus 5. What is the limit of this problem? Let's find out. Let's use the green marker just for funsies, why not? May as well get some different colors up in here, right? Once again, we have a factor up here in the form of ax squared plus bx plus c, which means that this is factorable into x and x. like that, like we just did in the last example. Meaning that we can turn this into two factors that multiply by each other to equal this and possibly simplify our problem down. Let's try this out and see if we get our factors simplified. Okay, so let's factor x squared minus 2x minus 15 is equal to 0. I'm going to ask you the same question I did last time. What two factors can add up to be negative 2 and multiply to be negative 15? One way to think of this is whenever we want to multiply to equal negative 15, we could find some factors of negative 15. So some of the obvious ones would be 1 times 15 equals 15. But what are the other two common factors of 15? That's right, 3 and 5. But you may also notice that this 15 is negative, so one of these two also has to be negative. So it could be either 1, it could be negative 1, it could be negative 5. We'll just use that as the example here. Now this one is piquing my interest. 3 times negative 5. That does equal negative 15. If we add negative 5 to 3, we get negative 2, which means that 3 and negative 5 are our factors. So x plus 3 and x minus 5 equals 0. And just to make sure, we have x times x, which is x squared. We have x times negative 5, which is minus 5x. We have x times 3, which is plus 3x. And we have 3 times negative 5, which equals negative 15. Adding these two together, we get x squared minus 2x minus 15 equals 0, which is the same as what we started with. So let's change it into our factors. We have the limit as x approaches 1 of our two factors. So x plus 3 and x minus 5, all divided by x minus 5. And just like last time, you may notice that we have an x minus 5 on bottom and an x minus 5 on top, which means these two cancel out. So now we simply have the problem, the limit as x approaches 1 of x plus 3. Once again, we can simply just plug in whatever x is approaching for x, in this case 1. So this will equal 1 plus 3, which is equal to 4. And that is the limit as x approaches 1 of x squared minus 2x minus 15 divided by x minus 5. Let's do one more example for today's video. In this example, I want to highlight that you don't have to have your function in the form of ax squared plus bx plus c to utilize the factoring rule. Let's do an example now where we don't have to use that. Let's say we have something like x squared plus 3x divided by x. And we have to find that function limit as x approaches 2. What can we do to make this problem a little bit simpler? Well, we can factor the top. You may notice that the top has an x in both parts of it. So we can change this limit problem into the limit as x approaches 2 of x times x plus 3, and then divide that by x. And once again, you may notice that we have an x on top, or an x on top and an x on bottom. And once again, we can cancel those two out, which means this problem is actually just equal to the limit as x approaches 2 of x plus 3. Once again, to solve limit problems, we just have to plug in whatever x is approaching. So we can plug in 2 for x. So this is just equal to 2 plus 3, which is equal to 5. And 5 is the limit as x approaches 2 of x squared plus 3x divided by x. In today's lesson, we're going to learn how to solve limits by rationalizing. Solve limits by rationalizing. Rationalizing. This is a long word. Hold on. We're going to learn how to solve limits by rationalizing. So why would we do rationalizing? The strategy of rationalizing a limit function over something like factoring, or for that matter, just plugging in whatever x is approaching to x. Well, I'm going to use my first example to show you why. In our first example, we have the limit as x approaches 0, that's always fun, of the square root of x squared plus 9 minus 3 divided by x squared. Now, if we were to simply just try to substitute this in, we would run into a problem. One of them is probably really obvious to you. Let's substitute in 0 and see what happens. We end up having the square root of 0 squared plus 9 minus 3 divided by 0 squared. That's already a problem because 0 squared is going to equal 0, so we for sure have a 0 on bottom. But what about on top? What do we have on top? Just to take a look and see what we get. Well, we end up getting the square root of 9 minus 3, which is equal to 3 minus 3 divided by 0, which is equal to 0 divided by 0. And that is a major dead end, and we know that we can find a limit for this problem, or we probably can. And we're going to try one strategy to see if there actually is a limit as x approaches 0 of this function. So where do we go from here? How can we manipulate this function in order to make it possible to solve without changing the actual value of this function? Well, what we're going to do is we're going to use what's known as the conjugate. The conjugate. Conjugate. Now, what is the conjugate? Well, it's a bit easier to explain with an example. Let's say we had the square root of 2 plus 7. The conjugate of this is the square root of 2 minus 7. All the conjugate is essentially this middle operation, this plus or minus. They're just flipped. They're interchanged, if you will. So the conjugate of square root of 2 minus 7 is square root of 2 plus 7, and the conjugate of square root of 2 plus 7 is the square root of 2 minus 7. Well, we're going to utilize this fact in order to simplify our problem down without actually changing the value of our function. And I'll show you how we're able to do this without changing the value of our function. What we're going to do is we're going to multiply this by the conjugate of the numerator. So why are we taking the conjugate of the numerator? Well, it's got a square root in it, and we definitely don't want to deal with that, or we want to minimize it as much as possible. So let's multiply the top by the conjugate. Our conjugate is x squared plus 9, the square root of x squared plus 9, and all we have to do is change this to a plus sign, plus 3. Now, here's the problem. If we were to just do this, we would be fundamentally changing what this function is equal to. So what we need to do is multiply by 1, which means this bottom needs to be the same thing. To explain this further, the square root of x squared plus 9 divided by the square root of x squared plus 9 is equal to 1. It's the same thing divided by itself. And 3 divided by 3 is also equal to 1. So technically, we are just multiplying by 1. We are not changing the value of this function at all. The conjugate is a sneaky little trick we can use to change the value of this without ruining this function's original value. We don't want to change that at all. We just want to multiply it by 1 and make it look different. Now what we got to do is multiply this by this, and that's going to require FOILing it out. So let's do that over here. We have the function, the square root of x squared plus 9 minus 3, and we are multiplying that by the square root of x squared plus 9 plus 3. So what we're going to do is we're going to multiply each one of these by each value, and we're going to FOIL it out. So the square root of x squared plus 9 times the square root of x squared plus 9 is just equal to x squared plus 9. A square rooted value multiplied by itself is just whatever value is inside the square root. That's a nice little trick to know as well. Next, we're going to do the square root of x squared plus 9 times 3, which is just equal to 3 times the square root of x squared plus 9. And now we're going to FOIL for negative 3. Negative 3 times the square root of x squared plus 9 is equal to negative 3 times the square root of x squared plus 9. And negative 3 times 3 is just equal to 9. Oh, that should be a plus sign there, my bad. You may notice that these two values cancel out, so boom, we don't got to worry about that no more. Oh, another mistake over here. This is supposed to be a minus 9. This is a minus 9 because negative 3 times positive 3 is negative 9. That makes a little bit more sense because now our 9 and our negative 9 cancel out. Cross that out. So our numerator is just equal to x squared after all this factoring stuff. And that sure is a whole lot nicer than this mess over here. Now let's do the denominator. And in fact, the denominator is going to be pretty simple. So we have x squared times the square root of x squared plus 9 plus 3. And I'm not going to change that at all. This is just going to be our denominator, and that'll make more sense in just a second. So let's put our numerator and denominator together and back into our limit problem. I'm going to grab my other pen. So now we have the limit as x approaches 0 of x squared on top divided by x squared times the square root of x squared plus 9 plus 3. And you may notice that we have an x squared on top and an x squared on bottom, and those two will cancel. So now our new function is simply the limit as x approaches 0 of 1 divided by the square root of x squared plus 9 plus 3. And this will not turn into 0 divided by 0, and if we were to plug in 0 here, we would get the square root of 9 plus 3, which will also not equal 0. So now that we have a much simpler function that will not equal 0 divided by 0, let's plug in 0 to our function. So this is now equal to 1, that doesn't change at all, divided by the square root of 0 squared plus 9, all, and then add 3 to that. So let's simplify this down. This is equal to 1 divided by the square root of 9 plus 3, which is equal to 1 over 3 plus 3. And our final answer for the limit as x approaches 0 of x squared plus 9 minus 3 divided by x squared is equal to 1 over 6. And that is the limit. And we are able to find this limit because of rationalizing. Now, I know it looks like a really long process, and I won't even lie, this step is kind of a pain, but it goes by really fast with a lot of practice. And in fact, we're going to do one more example for this video just so you get the idea down. Erasing, erasing. Our second and final example for this video is the limit as x approaches, and let me check my notes, as x approaches 2 of square root of x plus 2 minus 2 divided by x minus 2. Now the obvious red flag here is if we plug in 2 for our x values, we get 2 minus 2, which is equal to 0. Still can't divide by 0. That hasn't really changed in the last 10 minutes. We also end up getting 2 plus 2 under the square root. The square root of 4, which is 2 plus 2, is equal to 2. 2 minus 2 equals 0 divided by 0. We're in the same predicament as last time. But we can also solve this with the same strategy we used last time. Let's use the conjugate of this numerator and make this problem rational. So we can once again multiply by 1, in other words, multiply by the conjugate on top and bottom. So that is equal to square root of x plus 2 plus 2 divided by the square root of x, x plus 2 plus 2. And once again, we're going to have to FOIL and do that whole process, but I'll walk you through it. Let's do that over here. First, we're going to do the numerator, which is equal to the square root of x plus 2 minus 2 times its conjugate, which is the square root of x plus 2 plus 2. Foiling this out, we have the square root of x plus 2 times the square root of x plus 2. The square root of two values that are the same multiplied by each other is just whatever value is within the square root. So this is just x plus 2. Now we have, next we have the square root of x plus 2 times 2. So then we just have 2 times the square root of x plus 2. Next we have minus 2 times the square root of x plus 2. And lastly, we have negative 2 times 2, which is equal to negative 4. Once again, these two will cancel out. So then our value just turns into x plus 2 minus 4, which is equal to x minus 2. And this will be our numerator. Let's do the denominator now. Our denominator is simply, let me get my red pen out, x minus 2 times square root of x plus 2 plus 2. And once again, I'm not going to simplify this because you may already notice that some values are going to cancel out. So let's rewrite our limit problem from earlier with our new numerator and denominator. All of this is equal to the limit as x approaches 2 of our numerator, x minus 2, divided by x minus 2 times the square root of x plus 2 plus 2. Just like last time, we have a numerator and denominator value that cancel each other out. Bada bing, bada boom, just like that. So now our new, equation is the limit as x approaches 2 of 1 divided by the square root of x plus 2 plus 2. And just like last time, if we were to plug in 2 for x within here, we would get 2 plus 2, which is equal to 4. The square root of 4 is just 2. 2 plus 2 is not equal to 0, so we won't divide by 0, and our top function is just 1, so obviously that won't be 0 either. And in fact, let's plug in x approaching 2 for all of our x values in order to solve this limit problem. This is simply equal to 1 divided by the square root of 2 plus 2 plus 2, which is equal to 1 divided by the square root of 4 plus 2. And I'm kind of running out of room down here, so forgive me for this, but we're going to move over here. So this is now equal to 1 divided by 2 plus 2. So the limit as x approaches 2 of the square root of x plus 2 minus 2 divided by x minus 2 is simply equal to 1 divided by 4. And that is the answer to our limit problem. In today's video, we're going to be talking about special trig limits. Special trig limits. What are special trig limits? Well, there are some limits that we can solve without having to do all of the math, because there's a certain identity that we can use to solve the limit. This will be much easier to explain visually, so let's get started. There are exactly two special limits that we can use, and I'm going to write them over here. This is limit number 1, the limit as x approaches 0 of sine ax divided by ax is equal to 1. And the other special trig limit is the limit as x approaches 0, 1 minus cosine ax divided by ax, and this is always equal to 0. Let me explain what all of this means. So first of all, we have the limit as x approaches 0 of sine a of x divided by a of x, and that always equals 1. A is a constant, and this constant has to be the same within the sine of a of x and on the bottom a of x. If we can get our limit into this form, this will always just equal 1. Instead of plugging in the messy numbers and doing all that work, we just already know what it equals. It's very convenient. And the same applies for this limit, the limit as x approaches 0 of 1 minus cosine ax divided by ax. Once again, this ax and that ax have to be the same thing in order for this entire limit to just equal 0. Instead of plugging in all your numbers and doing all the math, we already know what this is going to be equal to. Today we're going to do one example of each of these special trig limits, and let's start with the sine example. And just for fun, let's use the green pen. Why not? The example we're going to start with is the limit as x approaches 0 of sine of 3x divided by x. What is this limit? First, I want you to notice that x is approaching 0, which means we cannot just substitute in x to solve this problem. If we were to just substitute in x, we would get 0 on the bottom, and we cannot divide by 0. So we're going to have to use a different strategy. We need to make this and this be the same thing. And in other words, we need to make this x on the bottom turn into 3x. How might we do that? And more importantly, how do we do that so that way we don't change the value of this function? That's a really good question. Well, just like in my last video about rationalizing, we could do something where we technically multiply by 1, but we're actually manipulating the function to just be a little bit different, but still have the same value. In this case, what we're going to do is we're going to multiply this entire inside function by 3 divided by 3. In other words, times 3 on top and times 3 on bottom. And this changes our limit into the limit as x approaches 0 of 3 sine 3x divided by 3x. And notice that we basically just multiply by 1. 3 divided by 3 is just 1. And let me put a little multiplication symbol there just to clear that up. But we're still not there yet. If we were to still plug in 0, we would get 3 times 0 on the bottom, and that is, well, still equal to 0. Plus, we have this pesky 3 on top, so we're not even in this form yet. So how can we get rid of this 3? Obviously, we can't just divide it out again. That would undo what we just did here. Well, this is actually a scalar. And if you watch my video about properties of limits, we know that we can pull scalars out to the limit and to the front. So this changes our limit to 3 times the limit as x approaches 0 of sine of 3x divided by 3x, and parentheses. And now we are in the form of sine ax divided by ax. Isn't that wonderful? So now we know that this entire limit is just equal to 1, which means that we just have the problem 3 times 1, which is equal to 3. And that is the limit of our problem. Let's do one more example of this limit, but instead we're going to use the red pen. So in this one, we're trying to find the limit as x approaches 0 of sine of 4x divided by 5x. What is this limit equal to? Well, you may notice that if we were to just plug in 0 again for our x values, we would get 5 times 0 on the bottom, which is equal to 0, and we still cannot divide by 0. That hasn't changed since last time. But our x on top and our x on bottom are very similar, so we just need to change this into that. In other words, we need to make them the same in order to get it into this form. What can we multiply this by on top and bottom in order to make this and this the same thing? Let me show you. If we multiply this function times 4/5 and 4/5, remember 4/5 divided by 4/5 is just equal to 1. We didn't actually change the value of our function. Our limit now turns into the limit as x approaches 0 of 4/5 sine 4x divided by 4x. Now we're getting somewhere, but once again we still have this pesky 4/5 in the front that prevents us from getting into this form. But just like in the last problem, we can pull this out to the front knowing our rule of scalars or that property of limits. So now our function is just equal to 4/5 times the limit as x approaches 0 of sine 4x divided by 4x. And now that we're in this form up here, we know that this inside function is just equal to 1, which means our whole problem is just 4/5 times 1, which is equal to 4/5. And that is the limit of our problem. Now let's do one example using this version of our special trig limit, the cosine version. In this example, we have the limit as x approaches 0 of 10 times 1 minus cosine of x divided by x. What is this limit equal to? Now you may notice that we're almost in this form. We're not all that far off. We just had this pesky 10 at the front, and it turns out we can still pull this constant value to the front of our limit. So this now turns into 10 times the limit as x approaches 0 of 1 minus cosine of x divided by x. And just like before, we have the same x value inside the cosine as on the bottom. In other words, it satisfies this condition, which means that this is all equal to 0. So now our function is just 10 times 0, which is equal to 0. And that is the limit of this function. In today's video, we're going to learn about the squeeze theorem in calculus. Now, the squeeze theorem is used to solve certain limit problems, and it also has a much better name than squeeze theorem. This theorem is also known as the sandwich theorem, which is objectively a better name than squeeze theorem, because we use squeeze in all sorts of things. When are you ever going to be able to apply a sandwich to calculus? What is the squeeze theorem? Well, this is a little bit easier to show with a visual example. Let's say we have a graph like this. Up here we have the function, something like that. It goes on from there to there, and this function is f of x. Now below it we have a function that looks something like this, and this function here is g of x. And between both of these functions we have the function h of x. It is between this function at all times. And let me write that out up in this corner. g of x up here is always less than or equal to h of x, which is always less than or equal to f of x. What about this can we do to help us solve limit problems? Glad you asked. Since we know that h of x is always between g of x and f of x at any given point, we know that at anywhere along this line, the limit of this function is always between these two, which helps narrow it down from literally infinity to a given plane. But more importantly, whenever these two limits equal each other, this is also equal to these two limits. There's two conditions the squeeze theorem must satisfy in order to be used to solve for a limit problem. Thing number one is what I just wrote over there. It has to satisfy this condition. G of x, our bottom function down here, must always be less than or equal to h of x, and h of x must always be less than or equal to f of x. That's condition number one, which we have satisfied here. It may not show up great in the drawing, but this h of x is always between f of x and g of x. And condition number two, the limit of x approaching whatever constant of g of x must equal the limit as x approaches c of f of x. And both of these limits must equal L. In other words, the same thing. And if these two limits equal each other, the limit of h of x is the same thing, because based on this rule, it will always be between these two. And let's just say that g of x is 2 and f of x is also equal to 2. This limit must equal 2. That's what the squeeze theorem is used for. If we know that h of x always lies between these two functions, we can find a point where h of x must equal these two. And this will probably make a little bit more sense when we do a mathematical example. So let's get started. I'm going to leave these conditions up here on the side so you can look at them while we do the problem. So the example we're going to use today is the limit as x approaches 0 of x squared times sine of 1 divided by x. What is the limit of this function? Well, at a glance, we're not just going to be able to solve it just by looking at it and be like, oh, it's just 3 times 2 equals 6. No, if we plug in this 0, we're going to get an undefined function here because we cannot divide by 0. So we're kind of stuck. So how may we go about solving this problem? Well, I want you to notice something. We have this outer function and we have this inner function, x squared and sine 1 of x. And more importantly, I want you to notice this function. The function of sine of x looks something like this. Let me get my blue pen out so you can see the graph a little better and extend this way over here. So this is what the function of sine of x looks like. It just goes up, comes back down like that forever and ever, going both ways, but I only need to draw it on one side. The highest this function will ever get is y equals 1, and the lowest this function will ever get is y equals -1. That is the balance of the sine of x equation. And as you can see, we are squeezed between two numbers, and we can apply the squeeze theorem to this problem. So I'm going to erase this graph so I have a little bit more room, and let's solve the problem. So based on the graph we just had up here a minute ago, we know that sine of 1 over x will always be greater than or equal to -1. Sine 1 over x. And let me make that look more like an S. That looks like a G. Sine. Okay, and based on the graph, we also know that the sine of 1 over x function will always be less than or equal to 1. So this function, this inner function here, sine of 1 over x, will always be between these two values. So now we've narrowed it down from -infinity to infinity to -1 and 1. That's a couple less numbers to work with. But you may notice that this actually isn't the function we have in our limit. We have an x squared times sine of 1 over x. So how can we change our sine of 1 over x to equal what we have up here while also not changing what it's between? That's right, we can just multiply everything by x squared. So we got to apply it to everything. -1 times x squared is -x squared, which is always less than or equal to x squared sine of 1 over x, which is always less than or equal to x squared. And at this point, we can actually solve the problem. How are we going to do that? Well, we can plug in our x value for x squared and x squared. So we know that the limit of -x squared as x approaches 0 is just negative times 0 squared, which is always less than or equal to x squared sine 1 over x, which is always less than or equal to, plugging in 0 here, 0 squared. And you may notice that -0 squared is just 0. And you may also notice that 0 squared is just 0, which means that this function, let me just bring it over here, apologies, I kind of ran out of room down there, is equal to 0, which is less than or equal to x squared sine 1 over x, which is always less than or equal to 0. And well, these are the same. We've squeezed this function between two other functions, which means that this must also equal 0 in order for this to be true. So this limit is actually equal to 0. And that is the limit of our problem.